Recording is rolling. It's Wednesday, August 17th. You guys remember this week I'm taking to cover the basics that were basic math skills that you guys are definitely going to need all throughout the year. So a couple days back we did algebra. I was short a couple of things I want to do with you guys that I'm going to fill in today. Right? And then yesterday focused on trigonometry and vectors and vector components, which involves a lot of trigonometry, is huge in physics. That ended up taking longer than I thought it would. So actually today, most of the time, I'm going to give you guys to work in teams, help each other out, and finish this page both sides. And then tomorrow I'll start on this science and measurement and scientific notation, dimensional analysis, all that type of stuff. And we'll see where we are. Yeah, so that's going to be a bump to tomorrow. All right, so before I get you guys going on this trigonometry, picking up where we left off yesterday, we go back the day before to algebra, because there's one more thing I wanted to hit that's going to be a really big important skill, especially for AP physics, which you guys are. All right, so you guys remember doing like graph linearization? Last week, we did this example with measuring circles, like properties of circles. And one of the formulas that ended up popping out of the graphs was area equals pi r squared, which you guys have known since like elementary school probably, right? For a circle, area of a circle is pi r squared. Okay? And then I had you guys measure area and radius. And if you graph area versus radius, area, say in square centimeters versus radius, say in just plain centimeters, right? What shape curve did that make? Yeah, parabolic relationship. It's like a parabola, right? So if you double the radius of a circle, what happens to the area? It doesn't double. It gets 4 times as big, right? So you go for like from here to here. This is truly a parabola. From there to there. You guys see? Oh, actually, I got that pretty close, I think. You guys see for like some radius, get that? But if you double the radius, you get 4 times as big, right? Because look at this relationship. If you throw a factor of 2 on this r, and then you double the r, doesn't that factor of 2 also get squared? What's a factor of 2 squared? 4 times. Hey, what if you had 3 times the radius? What would happen to the area of the circle?
9 times.
9 times. Right? But then, see, we did another graph. I know this is going back to the last week, but I'm about to connect skill to we're about to do a bunch of other things. What if you did area versus not the radius, but the square of the radius, like radius squared? So it's like centimeter squared, right? That's the unit. Notice I've labeled variable and unit on each set of axes. Right? So this is a different type of graph. It might be referring to like the same circles, the same sets of data. Right? What did this graph look like? Linear. Right, so you could graph all different radius. You square each radius. You find what is the area. Right? Oh no, if it was perfect, it might have been lined exactly like that. Now, realistically, your measurement data is going to have some points that kind of misalign. Right? Hey, and furthermore, what is the slope of this line? Pi, 3.14. Yeah, so I'll just call it pi. Because look, it looks like y equals mx. Okay, so here's your y. Well, actually, let me write this over here. Area equals pi r squared. So it's like your y value. This is like your x value. This is, well, I'll write out the word slope. If you were using algebra, it'd be m for slope, but we use m for like a ton of things. So, right? Slope times x, right? You guys get that? Okay. Right, now, that's a refresher from last week. Right, you guys ready for some new ones of these? Right. So what about here's a formula that you guys are going to see by next week. I want to get to you guys. X equals 1/2 at squared. Right. Now, if you did, what do you guys think the t stands for? Time. What do you guys think the x stands for? Displacement. What do you guys think the a stands for? Acceleration. Right. And you're probably looking at what? Why? What? Where's 1/2 coming from? This makes sense in time. I'm kind of getting ahead of stuff, but I really would just want to use this strictly as an algebra exercise. You're not really supposed to. You guys are going to put together this formula yourselves based on some lab data. It's all going to click. Oh wow, if you graph x versus t, suppose you did that, like x versus t, maybe like meters, and this could be like seconds, right? Then what do you think that graph would look like? Would it still be a parabola? Yeah, it's like square relationship. Right. Now, how could you linearize this? And there's more than one correct answer. But here, give you guys a moment here. help each other out, linearize that graph. How can you manipulate the variable, the axes? And it's not going to be x versus t anymore. The axis is going to be a little bit different. So this one looks like this. How can you linearize this? So you could just do x versus t squared. Couldn't you do that? Right? And if you did, okay, so if you did x versus t squared, then that would line up in a straight line. Right? And what would the slope of that straight line be? 1/2 a. Okay. Let's go one more step. Can you linearize it specifically in such a way that the slope is exactly equal to this right here, just this a? How about this? What if you, and there's more than one way to do it. Here's one way. Can you cross multiply the two? Make like 2x equals a times t squared. Look at that. Y equals m x. Y equals mx, right? Where m is like the slope. So if you did 2x, which could be in meters, versus t squared, which would be in square seconds, that would line up in a straight line in such a way that the slope is exactly equal to what again? Yeah, this acceleration a. Okay. Thank you. All right, how about let's try just a couple more of these. What if you? How about this one? Right, I'm gonna pick one that is no longer on the AP exam, and but we'll do this very briefly in spring semester. Suppose you have a wire. That could be a wire like blown up, right? And this wire has a certain cross-sectional area, capital A. It has a certain length called L, and let's say it has some resistivity I'll call rho. So this looks like a curly P. It's a Greek letter, rho. We'll also use this character for density in a different context. Right? But it's like resistivity. I'm just telling you guys what these are. And then from end to end, there's going to be some amount of resistance in that wire. Okay? And that resistance is equal to the resistivity. How about this? If the wire is longer, do you think there's going to be more resistance? Yeah, in fact, that's linear relationship itself. And what about this? If the wire is really fat, do you think there would be less resistance? And if that's true, then between this resistance and this cross-sectional area, would that be an inverse relationship? The greater the area, the less the resistance. How do you write that as an equation? Over A. Yeah, there you go. Okay. Now, I want you guys to, on a set of axes, let's do, there's more than one answer to this question, so let's do two solutions. Right. Can you linearize this data so that the slope is equal to this density rho? Linearize the data so that the slope is equal to 0. Okay. So you got lots of wires, you got lots of cross-sectional areas, lots of different lengths, lots of different resistances. Let's say you have like 100 different wires, and you get all these measurements put in a giant table. But it's all the same material. It's like we're using the copper wire over and over because that could be a material property, resistivity of like copper. So material property. I want to figure out how can what can I put on each axis? And there's a ton of variables floating around here. What can I put on each axis so that the data linearizes and the slope represents the resistivity? Who figured out one solution? What's one way to do it? What could you put on the, Jack, what do you think could go on the vertical axis? R. Yep, you could put R. And what could you put on the horizontal axis? L over A. L over A. Yeah, exactly. Okay, just look at that. Isn't that like Y equals MX? Y equals MX, and then your X is just L over A. Right? So resistance is going to be in ohms, and L over A. I bet you guys can figure this out. What do you measure length in? Meters. What do you measure area in? Meters squared, square meters. So meters divided by square meters. Could that be, what was that going to be? Meters divided by square meters. Meters.
1 over meters.
1 over meters. Yeah, 1 over meters. Okay. Or you could also call that meters to the -1 power. Same thing as 1 over meters, right? This this and this are all the same thing. Okay, guys, go ahead. Yeah, and this would in fact line up in a straight line. Okay. That's not the only where the slope is equal to the resistivity rho. There's at least one more way to do it. Can you guys think of a different way to also linearize the data? Yeah, what do you think, Rick?
R on the y-axis.
Okay, so if R is on the y-axis, what do you think for the x-axis?
Rho over A.
Over. Okay, yeah, you could do it. You could do rho over A, and then the slope would actually be L. So that would be true, and then that would tell you something about like the length of wire. Now that would be assuming if you have like a constant length wire, so all your wires like the same length, right? Now in the premise I'm trying to show you guys, and I'm kind of gets kind of fast. Suppose like you had a bunch of different shaped wires, but they were all made out of copper, which means they all have the same rho. Because notice here, if you're getting at one, this line has the same slope everywhere, right? So that implies that you are using like the same material because rho would be a material property, like the resistivity. You guys think that a copper wire and aluminum wire have different resistivities? Right. So how about this? This is a little tricky, but what if you took that cross-sectional area and you cross-multiplied it up? And you did area times resistance. And this might be in some like, well, resistance would be ohms, areas, square meters, right? And then you just put plain L over here. That'd be like A times R equals rho times L. Y equals MX. You guys see that? Y equals MX. So still straight line relationship. Here's all your data points, measurements. Okay. And then the slope is still resistivity. Okay. You guys see that? Okay. Okay. I'm going to do one more of these with you guys, and then we'll switch back over to trigonometry. All right, let's do a real tricky one. All right, this one's gonna come into play depending on where things land, either December or January. Okay. Again, the physics we're getting way ahead of ourselves, so but I'll tell you guys a little bit of the story anyway. Suppose you have a pendulum. Let's say put all the mass of the pendulum in the bob. Here's the length of the pendulum. And do you think it takes some time to swing back and forth once, some time t? Right? And do you think that the time it takes to swing back and forth differs depending on what planet you're on? Like if you're on Earth, maybe it's like swing, 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 swing. Or, so like 1, 2, 3, 4. On the moon, do you think it'd be like 1, 2? Think everything's a lot slower on the moon? Right. Huh. So something to do with gravity field. That's what I'm trying to get at. Like some gravity field probably has something to do with the motion of that pendulum, right? Okay. And if there's no gravity, you just like hang out there, not moving on. Right, so I'm giving you guys way too much info, so you're supposed to figure this out yourselves many months from now, but here's what it ends up being. 2 pi times the square root of L over G, right, for the time period. Right. Ooh, interesting that the mass of the bob is not actually part of that pendulum equation. Right. How about this? Can you linearize this so a graph so that the slope of a straight line graph, so something to do with the direct relationship, represents the gravity field of the planet that you're standing on. So now you can go to any planet, you can break out lots of different pendulums, different lengths, get lots of different corresponding time periods, but it should all line up in a straight line and tell you the gravity field of the planet. I'll give you guys a minute on this one. I have to do some algebra manipulation in terms of variables.
G the slope?
G is the slope. Yeah, G is the slope. Take form y equals mx. Ooh, yeah, you guys hear that? Right, so if you didn't figure that already, yeah. Liaison on this, you guys are going to some do like squaring something, right? That would help you like unbury that G. So yeah, gonna be some squaring going on. All right, you guys stay a step ahead of me. I'm gonna start checking through this.
Good morning, Hawk. At this time, all rosters have delivered, and we ask that all of our teachers conduct their 6-day count. We use the name of any student on your roster that you have seen at any time since the start of the school year, even if they're absent today. Please cross through the name of any student that you have never seen the whole year. Then please take your schedule to the door. Thank you so much. Have a great day, Vera. So hot.
Boom, done. We're back here. Did you guys possibly get this or something similar to this? Right now, that 2 pi quantity squared, you could have left on the other side. That'd be okay. This is one of maybe like a few ways you could do this. Okay? But here's your y equals mx. You guys see that? Right. Okay. So right, here's the story. You have lots of different pendulums, different lengths, and then you're calculating your timing. How much time does it take to swing back and forth? Right. So that would be one time period. Okay. And then now this is for one single planet though. We land on some planet like Mars, like, I wonder what the gravity field is. Okay. So then we make this whole table of data. Okay. And then for the x-axis, we're gonna go t squared, and it's gonna be in square seconds. For the y-axis, I'm gonna go 2 pi quantity squared L. That's going to be in what unit? How do you measure L? Meters, yeah, meters. And then the 2 pi is just a constant, so it's still meters. Okay. All right, so you get lots of time periods, square those. You get lots of lengths multiplied by 2 pi quantity squared, and then all that data will line up pretty well in a straight line. Where the slope is equal to what? G, yeah, the gravity field of the planet. Right? Okay. Did I get that? Right. Now, over the last few days, including just in the first few minutes today, I've thrown lots of different physics stories at you guys. Yeah, you've seen lots of different physics stories, lots of different variables. But the purpose of all this is just to show you how to navigate the algebra and to linearize these graphs, because that's a skill that AP cares about a lot. It's like linearizing graphs. Okay. All right. You guys good so far? All right. Let's switch over and do trigonometry. But let me do it this way. I'm gonna switch my screen real fast. Let's do let's see, present screen 2. Which I kind of muddled last time I tried to do that, but we're good. We're good. All right. And then let me mute this. All right. I've got a video that I'm just going to skip through to the important parts. Talking about scalars and vectors. We were talking about it yesterday. Right. What is a vector? What property does a vector have that a scalar quantity does not? Direction, right? So direction is important, right? For vectors, it is. Right. All right. So look, 3 meters to the right. Get a number, a unit, a direction. Right. So that'd be a vector quantity. Suppose you go 3 meters to the right and 2 meters to the left. What is your displacement overall from beginning to end?
1 meter.
1 meter, exactly. That's your displacement, 1 meter. And see that light pink vector? That's called the what kind of vector starts with an R? Resultant. You guys remember resultant? Right? Oh, look, those are connected tip to tail. Now this is all in one dimension, right? Now there's a different property you could do called distance, right? Now if you drive in your car, look at the odometer. How far would your car say you went on the odometer?
5 meters.
5 meters. And that's not displacement, that's called distance, which is a scalar. Right? Every once in a while I might slip up and use those interchangeably, or sometimes one is the other if you're just like moving in like forward in a straight line. But there you go, there's the technical difference. Displacement vector, all you care about is beginning point, end point, the difference. Distance, you can actually add up everything that you went. Okay, there's it. All right, how about, okay, all right, so got some numbers, boom. Right. Let's go to 2 dimensions. If you go 3 meters to the right, 4 meters up, what is your displacement from beginning to end? 5, because you guys recognize that's a 3, 4, 5 right triangle. You know Pythagorean theorem, but 3, 4, 5 right triangle. What distance did you walk? 7, right? 3 plus 4 is 7. Right. Okay, there you go. Displacement distance. Right. One more thing. How do you get? Where is it? That angle in the bottom left. How do you get that angle in the bottom left? You have a bunch of side information. You want the angle. How do you extract an angle from a bunch of side information? All right. Yeah, inverse tan 4/3. Yeah, all right. Rick got it. Inverse tan 4/3, right? Because tangent is like opposite over adjacent. So inverse tan spits you back out the angle, right? 4/3 because it's the 2 legs for tangent, right? Inverse tan, right? All right. We talked about tip to tail vector connection. You guys see that purple vector is going to be the resultant between the red and the blue. So walk right, then walk up. The resultant is the purple. Let's just say like, oh, had you gone straight line distance, right? Suppose you're like walking around a campsite or something, right? Could you do the blue first and then the red and end up with the exact same resultant, right? Notice the red and the blue are connected tip to tail. But what if you did tip to tail the other way? What if you did blue first and the red? You guys see it's the exact same thing, right? So vectors you can add together in any order. Oh yeah, okay. Displacement, Pythagorean theorem. Pythagorean theorem. So 3 squared plus 4 squared, take the square root. Yeah, because those are aligned up perpendicular, right? Now, if they weren't perpendicular, you'd have to take one. You'd have to introduce a coordinate system, break them down using sine and cosine, then add together the x components, add together the y components, right? And then it would eventually look kind of like this, right? It would just be a few extra steps in the middle. Okay. Right, so you have to break down stuff into right triangles first, right? Now, they're showing displacement vectors here in meters. Could be force vectors. What if you have a single object in the middle of the table and you're pushing on it all different angles at all different? Hey, you guys remember the monkeys and the bananas yesterday? 3 monkeys pulling at all different weird angles, and we broke those down into components, right? Or you could do this vector addition method with tip to tail vector addition. You guys see, what if you do this crazy path? Blue followed by red, followed by green, followed by yellow. And see the purple is still the resultant from the tail of the first to the tip of the last, right? Now this could be walking around a field, but maybe those refer to possibly force vectors like pushing on an object all different angles. So like maybe you have 1, 2, 3, 4 different monkeys pulling on a bunch of bananas all different, right? Looks like the green monkey's really weak, pulling really weak, right? Because the magnitude of the vectors is proportional to the length of the vectors, right? Now, what if you added those vector, besides the purple one, which is the resultant? What if you took the blue, red, green, yellow, and you just added them together, tip to tail in a different order? Okay, let me go ahead and roll this part of the video. Let's see. Let's watch this animation. They still create the purple resultant vector. What if you do? Notice those arrows did not rotate. They just connected tip to tail in a different order. Now it's yellow, green, blue, red. What about a different order? Green, red, blue, yellow. They still give you the purple vector, like I said. So that's adding together lots of vectors, tip to tail, and then you still get that same result. Okay, right, you guys good there? All right. So now let's take a look at these trig questions. Right, so I did do a couple of these with you guys yesterday on this side, and then I did one of these rows on this side. So let me do one more of each with you guys today, and then you guys will have the rest of the class period to help each other out finish these. Okay? So let's start with these generic triangles. There's 10 triangles. We did 2 yesterday. They refer to this model, which looks like a vector broken into components, doesn't it? Right. How about number 4? Ooh, that one looks interesting, right? So gave you an angle and one of the legs, interesting, right? Oh, these are Newton seconds, which is a unit of impulse. It's like momentum. It's like mass times velocity. Right. Hey, if you know what beta is, how do you get alpha?
90 minus beta.
90 minus beta, right? Because you guys know the 2 acute angles on a right triangle have to add up to 90 degrees. So what is 90 degrees minus this beta angle? I'm looking at this many degrees. Okay, right. And you guys do the same thing for your paper. Of course, everybody has different numbers. Okay. All right, so now we have the 2 angles and one of the sides. I'm going to break some paper up. It's paper time. So right triangle. We got. I actually dashed the. It's good practice to dash your component vectors if these are components of an original vector. Okay. Suppose there's like an impulse is like if you like bam hit something for a certain time, like force times time. Okay. That's what that unit says, isn't it? Newton seconds, force times time. Right? So if you bam hit something for a certain time. So what if I hit something up and to the right at a 29-degree angle from the horizontal? And you know that because this angle was given as 61 degrees, at least on my paper. Right? And we don't know how hard exactly, but we do know strictly in the vertical direction it ended up being, this is my number here. And then Newton seconds is the unit, right? So, okay. So that's the information I have. Right? You guys go okay so far? Right. Can you guys figure out the rest of that triangle? Right? There's different ways you could approach this. Just to move things along a bit. Let's say I play off the 29-degree angle. If I do something with tangent, I could get the other leg. And if I do something with sine or cosine to directly get the hypotenuse? Sine, because I have opposite, so opposite and hypotenuse would be sine. Right? Maybe I'll start with tangent. Why not? Right? So I know that tangent of 29 degrees equals 337 Newton seconds divided by side x. Here's side x. Right? Solve for x. Hey, can I cross multiply x and divide the tan 29 degrees down? Right? I'll break that down to 2 steps. X tan 29 degrees equals 337 Newton seconds. Divide the tan 29 down, x equals 337 Newton seconds divided by tangent of 29 degrees. Okay. No, this will work as long as your calculator is programmed in degrees. Make sure it's not radians if you brought in your own calculator, because calculator has to know how you're measuring angles. So what's 337 divided by tangent 29 degrees? That looks like 608 pretty much. And then it would be Newton seconds. So this would be 608 Newton seconds. Okay. Okay. I can believe that. I mean, that looks believable, right? Which is a good last step to do in any physics problem you solve. This is a really small acute angle. So less than 45 degrees. So this x should be larger than this y. Yeah, checks out. Okay. Last thing, what was the total impulse actually applied to some object? Okay, here, model for this, guys. Something like this. Okay, bam. That's kind of what just happened. Ooh, what's one way to get it? Pythagorean theorem. Sure, why not? Right. Or you could do sine play on these two, or cosine of these two from the 29-degree angle. Okay. So yeah, let's do Pythagorean theorem. I'll just do this on my calculator screen. The squared plus the squared equals the squared. So what is the square root of 608 squared plus 337 squared? That's 695, and then the unit would be Newton seconds. So that was the actual impulse that you would have originally applied. Then if you break that down into components, it's okay. You guys get the idea? All right. Guys good? All right. And let me model another one of these triangles on the side. Okay. So remember, this is where the science meets the math. Right? So this is, you're gathering empirical data, you're actually making measurements. Just had a nice big protractor here. It is lost. Well, I got my little backup. So I'm going to use, and look at that. All right. It's here sometimes, I guess. All right, so how about this Tesla triangle? Now, one thing I mentioned yesterday, and I'll go ahead and take care of right now, is that these triangles are a little bit small, especially if you have one of the larger protractors. So I'm going to go ahead and extend the legs, like especially this leg here, right? Because if you just extrapolate that might help you out. And I'll do for both of them. Okay, so remember, across hovering over the top of the table, it says whether to measure or calculate. Right? So 2 things to measure. You can measure angles, or you can measure lengths. Here's my nice big protractor. There we go. Okay. And then calculations, we're going to pull up the calculator. Right? So alpha in degrees. So I want to take this node of this protractor, park it right on this corner of this Tesla triangle. Right? Zero out this leg right there. Right? And then the hypotenuse will naturally sweep through. You know what? I changed my mind. I think these 2 triangles are similar. I remember these numbers coming up yesterday. Let me pick a different triangle. How about this? Did you say it's Curry? I knew at one point. Is it Murray Curry? His name after? All right. All right, so let's go alpha for Curry. So zero out this leg of the triangle, park the node around that corner, and yep, my triangle is a little bit too small, so I'm going to extrapolate the side so that it actually sweeps through something. Try again. Looks like 52, I think, 52 degrees. Or you could turn this upside down and try it the other way. So zero out the hypotenuse. And yeah, it's still showing, 52 degrees. So Curry, alpha, 52 degrees. Right? How about beta? I might actually have to extend this hypotenuse the other way. I could do that. Okay. Park this node right on this corner, zero out this leg. This sweeps through. It looks like 38, I think. Call it 38 degrees. Hey, what do alpha and beta add up to? 90 degrees. Right? As long as it's somewhere between 88 and 92, you're good. Unless you're in a math class, then they better add up to 90. But science, get a little bit of wiggle room. There's always some error in your measurements. So as long as you know that, right? Should be pretty close to 90. C, what is side C? Hypotenuse. This is 5.5, I think. 5.5. If you get something slightly different than I do, then that's fine. What is side A measured? I'm looking at 4.4, I think. 4.4. And then I'm going to skip a few cells and go to side B just to grab the last measurement real fast. That looks like 3.3. Oh. Whoops, did I say 4.4? I think I said 4.4. What did I say? Here, let me go back and remeasure A just to make sure. I'll call it 4.4 because I want to make a point here. Guys, 3.3, 4.4, 5.5. This curved triangle looks like it's going to be a what triangle?
3, 4, 5.
3, 4, 5. Yeah, scaled up by a factor of 1.1. All right, so now let's do some calculations. All right, so C times sine alpha. So if I do C, which is 5.5, times sine of, now don't mix up A and alpha, those are completely different ideas for different units. Okay? The centimeters is already given for all the lengths, it's already specified. Okay? So sine of 52 degrees, that is 4.33, so about 4.3. C times cosine beta. So what is 5.5 cosine of 38 degrees? That is also 4.3. And then reverse Pythagorean theorem, square root of c squared minus b squared. You guys remember from yesterday, if you rearrange the Pythagorean theorem, it also refers to one of the legs. Square root of 5.5 squared minus 3.3 squared is exactly 4.4. Okay. And then these last three cells, also calculation, c times sine beta. Oh, I should slow down a little bit because I do want you guys to see. You guys see that dark rectangle around each set of well, around these four and around these four, right? That's because within each row, they're all referring to the same side. That is one of the major points of even like making this file in the first place, that you guys can see that. See, if you take C and you multiply by sine of beta, that'll flip over from hypotenuse to the opposite leg from beta, which is side B, which is a different perspective on what I already measured to be 3.3. Right, so let's see if this works out. So what is 5.5 sine of this beta, 38 degrees? That is saying 3.39, I'll call it like 3.4. Okay. C times cosine alpha. So take my 5.5 cosine, now cosine alpha, that goes from the hypotenuse to adjacent to alpha, which is also side B. Hey, look at that. So alpha was 52 degrees, cosine of that. Look at 3.39 again, so about 3.4. Okay, and then reverse Pythagorean theorem. What's the square root of c squared minus a squared? Okay. So that's 5.5 squared minus 4.4 squared, and that is 3.3. So I think my measurements were off a little bit. Okay. If this was truly, I think it's really close to a 3, 4, 5 triangle. If it was truly a 3, 4, 5 triangle, do you guys remember what these angles should have actually been for that scenario? It's like 53 degrees and 37 degrees. So all 3, 4, 5 triangles have those angles specifically. Okay. All right. So we got a solid 15 minutes in here. Tell you what. How about this? Have at least 3 of these 5 completed, and also do all 10 of these on the side. Make sure you can work your way around a triangle. Oh, okay. So which one? The Lavoisier triangle? Oh, the little skinny one? Yeah, I'll do that. Okay, let me go ahead and jot this down. right, so here's your assignment, and I'm gonna pick this paper up. So assignment, right? So do 3 of the 5 measure and calculate triangles, and then do all 10 of the what I call the side of trigonometry puzzle, right? So of trigonometry puzzle. Okay, right, guys get that? Oh yeah, go ahead. An extra protractor. Yeah. Oh, you see that black bin right there? There you go. All right, I'll do it for you. All right, yeah. So here's a request. I'll go ahead and let's do this this little skinny triangle with OCA. All right, so gonna grab this little tiny alpha angle. So park this node right on this corner, and that looks like 7 degrees. I'm getting 7 degrees for alpha. Okay. Now beta, if it helps, you could extend this beta side. Okay. Right, park this node right on this corner, zero out this leg. Wait, okay, that looks like 80. Hold on. Okay. I think I'm getting like 82 degrees. Looks like something like that. 82 degrees. Okay. Check, make sure this makes sense. 7 plus 82, that's 89. That's pretty close to 90, so that'll be close enough. Okay. Side C.
Oh, that's on you.
Oh, you just do those? Okay. All right. You guys be okay from there? Okay. Oh, yeah, just sign up. I forgot to figure it. Yeah, I'll just get you a conventional pass. Okay. Yeah. You go. All right, and I will walk around, help you guys out, and end this recording right here. Oh, here, let me end it actually on. Just sign it here. And